Hello and welcome to today's lecture on MOS transistors. This is the second lecture on MOS transistor, and today I shall discuss on MOS transistor operation. And here is the agenda of today's lecture. First, I shall give a brief introduction about what I have discussed in my previous lectures for the sake of continuity. Then I shall discuss the fluid model, which has been found to be very useful in understanding the operation of MOS transistors. And as part of the fluid model, I shall consider the operation of a MOS capacitor, which is the most elementary building block of MOS transistors. Then I shall discuss about the operation of MOS transistor based on fluid model. And after that, I shall discuss the characteristics of MOS transistor without going into any mathematical expression or analytical analysis. I shall simply do that based on the fluid model, and after that the various modes of operation of MOS transistors will be discussed. This will be followed by regions of operation of a MOS transistors. You will see there will be 3 regions of operation of a MOS transistor, and it will be followed by highlighting some of the important parameters which affect the operation of a MOS transistor. Okay. I have already discussed in my last 2 lectures, I have discussed the structure of MOS transistors. I have also discussed how MOS transistors can be fabricated, and we have seen based on the structure of MOS transistors, we have 4 types of MOS transistors. These are NMOS enhancement type, NMOS depletion type, PMOS enhancement type, and PMOS depletion type. And we have we shall be using these symbols in our lectures. As I have mentioned, there are other symbols available which are also used, and you will find in different books different types of symbols are used, but these are the most commonly used symbols and which I shall follow in my lectures. Now, as I have told, today we shall discuss the operation of MOS transistors. The operation can be analyzed by using suitable analytical technique. That means, the operation of MOS transistors can be done from the by studying the semiconductor physics, based on semiconductor physics. That means, you have to understand the detailed and the detailed equations and detailed knowledge of semiconductor physics is necessary, and obviously later on we shall do that to derive the analytical expressions. But to start with, what we shall do? We shall be using very simple model which are not based on any analytical expression, complicated equations or anything. And this is somewhat similar to whenever we build a building or a bridge or a campus, we make a model essentially to visualize the overall layout or the structure or the basic functionalities of the system. And this can be very nicely done with the help of a very simple but very effective model based on fluid model. This fluid model, as we shall see, can visualize the operation of charge control devices. Charge control devices like BDDs, bucket brigade devices, then CCD, charge coupled devices, and MOS transistors are one of them. That means, MOS transistors are essentially charge control devices, as we shall see, and their operation can be very nicely explained without going into detailed semiconductor physics with the help of this fluid model. And you will see, you can understand the operation, this operation of MOS transistors can be understood even by a novice. Okay. So, what is this fluid model? This fluid model I shall be using is based on 2 very simple ideas. What are these 2 ideas? First one is, electrical charge is considered as fluid which can move from one place to another depending on the difference in their level of one from the other, just like a fluid. As we know, whenever we consider that in a container we have a fluid, and that fluid, as we know, if we connect them to another container, it will move from one container to another container depending on the difference in level. Similarly, as we shall see, charge will move from one place to another place whenever there is a difference in I mean there is potential difference between the two. And so, this is the first model. Electrical charge can be considered as fluid, and obviously, its behavior will be very similar to fluid, the way fluid like water, oil and various types of fluid behave as we see in our real world. Then another very simple idea is electrical potentials can be mapped into the geometry of a container in which the fluid can move around. That means, we shall see that inside the MOS device, that we have discussed the structure of a MOS transistor, and within the geometry of a MOS transistor we shall be applying some voltage, and that will create some electric field. There will be some electrical potential distribution. That electrical potentials can be considered as kind of container. So, the way they will map within the geometry of the device, they will be considered as a container, and within that container we can keep charge like a fluid. So, this is the basic simple idea that we shall be using, and this has been taken from a very famous book by Carver Mead and Lynn Conway. Back in 1980, they published one path breaking book, Introduction to VLSI System, and that was the first book on VLSI system, and that actually popularized VLSI fabrication technique among researchers, students. Before that, it was essentially the fab houses who were concerned with VLSI fabrication, but this book popularized VLSI system design among students, researchers and so on. Anyway, so this particular fluid model I have taken from that book. So, based on that fluid model, first I shall consider the operation of MOS capacitor. This MOS capacitor is essentially the most elementary building block of MOS transistors or MOS circuits, and as we have seen, a MOS capacitor is realized by sandwiching a thin oxide layer between a metal or polysilicon plate on a silicon substrate of suitable type as shown in this figure. Let me draw it for your convenience, a MOS transistor, MOS capacitor. So, the MOS capacitor. So, what we have seen when we fabricate MOS devices, we start with a wafer. This is the wafer. So, this is the wafer, and then we fabricate, we put silicon dioxide on top of that. So, this is the silicon dioxide, and on top of that we put polysilicon. So, this is the polysilicon. Okay, we can represent it by hatched area. This is the polysilicon, this is silicon dioxide, and this is your substrate, or you can say p type substrate. It can be n type as well, it does not matter. So, here we can consider this particular structure, which is nothing but a MOS capacitor, as a it can be considered as a MOS capacitor, and these two, polysilicon and this p type substrate, these two are representing two parallel plates. In a capacitor, as we know, parallel plate capacitor, we have two plates. You will equal two plates, and in between two plates you will put some dielectric material. So, here this dielectric material is silicon dioxide, which is an insulator. So, this is realizing a parallel plate capacitor, and normally, as you know, we apply some voltage across it, and in this particular case we apply positive voltage to this polysilicon, because it is a we have assumed that this is a p type substrate. Normally in NMOS transistor this is what we do. So, this is positive and this is negative. Now, based on this fluid model, what we can do, as we apply some positive voltage, this can be mapped within the geometry of the MOS structure. First of all, this voltage, whenever you apply a voltage, it will create some potential distribution in this substrate. So, it will be somewhat like this. So, we can map it within this. So, here it will be somewhat like this. So, this is the potential distribution. So, we can say this is the interface potential. And here, as you can see, this potential distribution has taken the shape of a container. So, this is the container where charge can be stored. How charge is stored? Whenever you apply a positive voltage, as you know, negative, I mean the electrons are induced on this area. So, there will be electrons on this, just on the opposite side of the insulator. That means, opposite in this particular on this plate, it will induce this positive voltage will induce charge, and that will be present in this area. And we can say these negative charges can be stored in this parallel plate, in this container. So, here you have got charge. Charge means in this particular case electrons. So, here electrons are present, charge in the form of, you can say, electron. You could have started with another type of capacitor where you could have applied negative voltage starting with n type substrate. In that case, this charge could have been holes. So, that is why I am writing charge and then mentioning electron. In this particular case, it will be electron, because most of our discussion will be around PMOS NMOS transistor, and of course, as and when necessary we shall discuss about PMOS transistor. So, in this particular case, this MOS capacitor will be having, I mean will be this, in this area it will be inducing some charge, and this charge will be present here. Now, this charge, the amount of this charge will be dependent on what? As you can see here, this charge will be dependent on two parameters. First of all, this particular area, I mean how big is this area? Essentially capacitance C, capacitance value, this amount of charge that is being stored here will be proportional to C. And another it will also depend on another parameter, that is your voltage, that is the voltage that you apply here. How it will vary? Suppose you keep on increasing the voltage, what will happen? This will actually push this electric field below. It will be somewhat like this. If you increase it further, it will be like this. So, that means the size of the container is increasing as we are increasing the voltage. That means, more and more charge can be now stored. If the voltage is more, charge will be more, and the shape of the container is changing to store more and more charge. So, as we know, Q is equal to proportional to C and V. This is very clearly visualized with the help of this model. Now, after these charges though these are essentially electrons, what will happen? This electrons will actually neutralize some of the potential, and as a result, in the equilibrium, whenever equilibrium condition is reached, the potential distribution will be somewhat like this. So, this red line, this is the potential distribution in the equilibrium condition, because these electrons will be of opposite, it will they neutralize the influence of the positive voltage that is being applied on the other side. So, you can see in the equilibrium condition, you can say these are all filled up with electrons. So, the potential will be somewhat like this. So, this is how we can explain the operation of a MOS capacitor, and as it is mentioned here, this fluid representing amount of charge and the presence of inversion charge, the surface potential is shown in B. So, this is the line, this is the line. So, which I have shown in this diagram, this one. So, this is the inversion charge, means originally as I mentioned, this was a p type substrate, there were holes present here, but this voltage that has been applied to the other side of the plate has induced electrons, which are known as inversion charge. Okay. So, this is the this is how the operation of a MOS capacitor can be explained with the help of a with the help of the fluid model. Now, let us consider the function of a MOS transistor. We can extend the basic concept of MOS capacitor to MOS transistor. What is the difference between a MOS capacitor and a MOS transistor? As you can see, the central portion is essentially the MOS capacitor, and of course, on both sides we have got drains and source. So, we can draw it starting from MOS capacitor. So, here the MOS transistor. So, we can start with same thing. So, this is the substrate, and here you have got your silicon dioxide, on top of that you have put the polysilicon, and then on both sides of it you will be having source and drain. So, this is p type substrate, then this is n plus and this is n plus. So, this will form source and this will form drain. So, I am assumed that I am taking electrical connections. So, I have put metals on top of this source and drain. So, this is the structure of a very simple MOS transistor, NMOS transistor. Now, in this particular case, what will be the corresponding interface potential? Let us see. So, this is the gate, this is the source, this is the drain, let us assume. Now, in this particular case, as you can see, this part is essentially the capacitor part. So, here you have got the polysilicon, on top of that metal has been deposited, this is the silicon dioxide layer. What will be the interface potential here? So, here also you will be having interface potential. To start with, let us assume that you have applied some voltage, the voltage that is being applied to the gate and the drain. I mean both gate and drain, they are at the same potential. They are at the same potential, and of course, you can apply that means these two are joined, and you can apply some positive voltage to the gate. So, this is the model that we will be using. So, whenever this voltage is 0 and the source and drain, these are at the same potential, then what will happen? We can say that these two are having infinite source of electrons. Since the source and drain, these are very heavily doped, they are considered as infinite source of electrons. How do you really represent an infinite source of electrons? We can consider them as n wells of infinite depth, and of course, so this is the, on both sides you have got n wells of infinite depth, and they are since they are potential, they are connected, tied together, the potential are same. Now, what about the middle portion? What will happen to the middle portion? In the middle portion, whenever this voltage is 0, obviously there is no electron present here, and the voltage will be somewhere here. I mean potential will be somewhere here. So, you can see the potential distribution in the gate region is somewhat like this. So, you can say that potential distribution will be somewhat like this. It will be somewhat like this. Now, in this particular condition, say this is figure number 1, this corresponds to V G B is equal to 0. That means, the gate voltage with respect to this, you can say source, as you know the source is connected to body, as you have already mentioned by using a P plus contact. Since source is connected to body, that is why G B is equal to 0. We have assumed that G B is equal to 0, and under this case we have a barrier. So, we have a potential distribution here. That means, here you have got infinite source of electrons, here you have got infinite source of electrons, as if we have got two containers of infinite two I mean two kind of two containers having infinite depth, and lot of electrons are present here in both the cases. But unfortunately, since the potential is above this level, these two are separated by this particular barrier. So, now although the source and drain are having infinite source of electrons, they are not connected. So, no charge can move from one to the other. Now, let us assume that let us keep on increasing the voltage, this base gate voltage. As you increase the gate voltage, what will happen? What we have seen in this particular case? This potential is pushed down. So, this interface potential will be pushed down. So, here also this will be pushed down, say this will correspond to say 2, this is corresponding to 3. Now, what is happening whenever it is 3? Say 3 is the situation where there is a condition as if these two are touching, I mean almost touching, and if it is little more than that, then these two will be connected. So, this 4 this 1, 2, 3 and 4, this potential 4 corresponding to a little higher gate voltage will correspond to a situation when these two will be connected to each other. But since their potentials are at the same level, there will be no flow of charge. That means, whenever the gate drain voltage and source voltage are same, although they are connected by a path, as we know that path is channel, there will be no flow of current, because their potentials are at the same level. So, since they are having the potential at the same level, no flow of current will take place. But the position where they are they are for a particular whenever this is 0 and whenever these two are almost touching, that is actually this what voltage we assign to it? We call it threshold voltage V T. That means, a voltage which when we apply to the gate creates a channel, creates a conducting path between the source and drain. So, that is the minimum voltage that you will require to connect the source and drain. In other words, that will create formation of the inversion layer. So, electrons are present here, they are connected to each other. So, the surface potential will be somewhat like this now. So, in equilibrium it will be like this. So, that means it will be like this. So, this is the situation where we are assuming that V dV drain voltage is same as base voltage, and we are varying the gate voltage, and as we have seen at some point of time these two are connected to each other, but no charge will flow because they are at the same potential. Okay. Now, let us go to the second situation. What is the second situation? In the second situation, what we shall do? We shall apply some higher voltage to the drain with respect to the source, and apply some voltage which is above the threshold voltage at the gate. So, these two, and then vary the drain voltage, and we shall see what happens in this situation. Let me redraw these figures to explain that. So, again it will be the MOS transistor operation. So, in this particular case, again we use the same structure, that means we have the substrate, and on we have the MOS capacitor, silicon dioxide, polysilicon, then source and drain. So, you have got N plus, and this is p type substrate, because we are considering a NMOS transistor, and here we have put some metal for taking connections, also some metal for taking connections, and here also some metal. Now, what we shall do, of course, as I have already told, this is P plus. So, this is connected, source is connected to it. Now, with respect to this source, we shall apply some positive voltage to the gate. That means V G B is greater than V T. V T means the voltage at which channel is created. And what about this voltage? We shall apply a variable voltage. This is positive, this is negative, this is positive, this is negative here. So, and this we shall be varying. So, in this condition, what will be the situation and the potential interface, and how the device will behave, let us see. So, here also you have got potential distribution, interface potential you can say. Again we shall be having two OLs, but in this particular case initially let us assume these two this voltage is 0, that means source and drain initial condition is say V G B V D B is equal to V S B is equal to 0. So, this is with respect to this body, 0 voltage is applied to the source and drain, and let us assume these are the potentials to start with. And as usual, as we shall see, these are the infinite OLs. Now, what we do, we have applied a gate voltage which is more than the threshold voltage. So, the gate voltage is somewhere here, Now, let us consider the situation when we shall be pushing this, increasing this drain voltage. So, drain voltage is gradually increased, and initially say this is the condition A, this is the condition for A, where drain voltage is same as gate voltage. Now, what we do, we simply apply V D B is equal to V S B plus delta, little more. As we increase it, what will happen? This, in this particular case, the charge, the distribution was like this, the potential distribution was like this. Now, as this drain voltage is increased with respect to source, it will be pushed downward. So, as it pushed downward, it will come here. Then what will be the potential distribution in the equilibrium condition? It will be like this, and we increase it further, say 3 is V dV is greater than, significantly greater than VSV. What will happen in this case? Say it has reached this point. Then okay, another point I should tell, whenever the drain voltage is made little higher than the gate voltage, and when the gate voltage is more than the threshold voltage, as you can see here there is a slope. Earlier it was horizontal, now you have got a slope. What this slope represents? Current. That means, the rate of flow of charge is indicated by this slope, and this amount of current that will be flow is dependent on this slope. Slope is not very high, so current will flow. So, in this particular condition current will start flowing, and as we increase it further, as you can see, this slope will increase. Now, we have reached this point, the slope is reaching maximum point, and whenever it is say condition 4, V dV is greater than V GB plus Vt, then what will happen? This will be the case whenever it reaches here. So, this is the condition where this V dV is equal to V GB plus Vt. So, at this point. Now, this is the condition 4, this is the condition, no. So, this is the condition 4 and this is 5. So, at this point, if you go further down, you can see at this point the slope is maximum. If it is pushed further, there will be no change in slope, because it has reached the maximum point. So, there will be no further change in slope even if you push it beyond this. That means, if the drain voltage is increased beyond this value, there will be no change in slope, and as a consequence no further increase in current. So, what is happening? We can consider these are mentioned here. Gate voltage higher than threshold voltage, as I have told. Drain and source are at the same voltage. This is the situation A. Then in B, drain voltage is slightly higher than the source voltage, as I have already explained. So, you have got a slope here, and drain voltage is higher than source voltage, as you can see here. It is more than the threshold, it is more equal to almost the V dV is equal to V SB plus VGB plus VT. And at this point, as you can see, this drain voltage is much higher than this, I mean V is greater than VGB minus VT. So, in this case you can see the slope has not changed from this, between in these two the slopes are same. So, no further increase in current take place. So, we have seen how actually current flow occurs in a MOS transistor. Can we now construct the characteristics of MOS transistor based on this model? Let us see whether we can do it or not. Characteristic. So, what I shall do on this, we shall put on this side, we shall put, we are interested in drain current IDS. On this we shall put VDS. So, we shall analyze the increase in drain current as we increase the drain voltage with respect to source, or it can be body. If source is connected to body, VDS is same as VDV, and for different gate voltages. So, for a particular gate voltage, as we have seen, initially the current increases, and as it reaches the point which is equal to VGB plus VT, then it remains constant for a particular gate voltage. Now, if the gate voltage is more in this particular diagram, what we could have done, we could have applied a higher gate voltage here. So, in that case if we apply higher gate voltage, this will barrier will be at lower. So, the maximum current that can flow will be more, because slope will be like this. So, more current can flow as the gate voltage is more. That means, whenever you apply a higher gate voltage, then the curve will be somewhat like this. So, this is for a particular gate voltage, say this is VGB1, this is VGB2, and you can increase it further, and you will get a curve like this VGB3. So, we can see we have been able to draw the characteristic of a MOS transistor without deriving any mathematical expression. Simply based on fluid model, we have been able to express the operation of a MOS transistor and how current can flow in a MOS transistor, and later on we shall see how it actually happens. Okay. I mean derive mathematical expression for this. Another plot is here, the current dependence of current on the gate voltage. So, we have seen here this gate voltage, this current is increasing as you are changing the gate voltage, sorry, this is G, GB1, GB2, GB3. As we increase the gate voltage, the current is increasing. Of course, this VGB1 has to be greater than VT, all the voltage has to be greater than VT. That is what is being shown here. That means, this curve shows that starting with VT, as we increase the gate voltage, these are essentially representing the saturation current, I mean these currents, and we can control the current with the help of this gate voltage. So, what we have learnt from this fluid model? From this fluid model, we have learned that MOS transistor can be considered as a voltage control device, and as we have seen, the current, drain current is dependent on two parameters. What are the two parameters? Electrical parameters, gate voltage and drain voltage with respect to source or body. So, by controlling the gate voltage and drain voltage, we can control the flow of current in the channel, and that is how MOS transistor works. So, this is as simple as this. Okay. So, after discussing the characteristics of MOS transistors, now we shall focus on another very important aspect, modes of operation, the modes of operation of MOS transistors. We have already explained the operation of a MOS transistor by using fluid model, and we have seen how and when current flow takes place and how the current increases and so on. And based on that, the operation of MOS transistor can be divided in three modes. First one is known as accumulation mode. Number one is accumulation mode. What happens when this mode is represented by what? When this gate voltage VGS is less than VT. What do you really mean by accumulation mode? In the accumulation mode, we have seen that initially this is the charge distribution as it is shown in this diagram. That means, you have got positive charges on the this polysilicon is heavily doped silicon. So, it has got holes, and then this is a p type substrate, here also you have got holes, and as we increase the initially this portion, this portion also will be having sorry, this is the silicon dioxide. You can see the entire portion, the p type substrate is filled up with holes. Now, as we increase this voltage, what will happen? This these portions will this positive voltage will induce electrons here, and they will neutralized some of these electrons, and as a consequence gradually this part will be devoid of any charge carrier. For example, in this case we shall reach depletion mode. Depletion mode is reached. Depletion mode is reached when VGS is equal to VT. You can see this channel region is completely free of charges. So, how we have reached this stage? We have reached this stage by gradually increasing the voltage, gate voltage from 0 to VT. As you increase the gate voltage from 0 to VT, this is the silicon dioxide, this is the polysilicon, and this is the substrate. We can see the channel region now are having positive charges when this gate voltage is 0, and as it is increased to VT, threshold voltage, we define the threshold voltage, onset of flow of current, onset of creation of inversion region, you can say. This depletion region is there where there is no charge carrier, current carrier, I mean those carriers, neither hole nor electron is present here. So, this is the depletion mode where VGS is equal to VT. Now, if the gate voltage is increased further, what will happen within the geometry of the device? As we shall see, it will induce electrons, as you have seen, and this will create what is known as inversion layer, or and that is why it is known as inversion mode. So, inversion mode is when VGS is greater than VT. When the threshold voltage, gate voltage is more than the threshold voltage, the device moves to what is known as inversion mode, and in this inversion mode we have got electrons present here, and as we know these electrons will be attracted towards drain if we apply a positive voltage to it, and current flow will start. So, for flow of current, this inversion mode is necessary, and before that, when this device is in depletion mode or in accumulation mode, no current flow can take place. Okay. And another operation we shall see, regions of operation. We have already discussed the characteristics. Here, characteristic of a MOS transistor. Now, the operation can be broadly divided into three parts, three regions of operation. What are the three regions of operation? First of all, first region is cutoff region. Cutoff region is accumulation or depletion mode, when no current flows between the source and drain, as I have already explained. So, in the cutoff region of the characteristic, no current flow, that means this is represented by this point A. This corresponds to the cutoff region. That means the no current is flowing, in this drain current is flowing. So, this is the point which represents the cutoff region. Then we have got second situation which is known as non-saturated region. Non-saturated region which is known as weak inversion mode, when the drain current is dependent on the gate and drain voltage. That means, here it is known in several names, linear region, weak inversion region, non-saturated region, these are essentially same. And in this particular curve, this part is essentially B. So, this is your non-saturated region, where, or it is also known as linear region, because current is linearly, almost linearly increasing, as you can see, current is linearly increasing. That is why it is also known as linear region. So, this is the second region where current can flow, but current is dependent on the gate voltage, as you can see, and also on the drain voltage. So, for example, this at this point, for the same drain voltage, for three different gate voltages, 3 different current. Similarly, for different drain voltage, you can see for the same gate voltage, the drain current is changing. That means, the drain current is dependent on two electrical parameters, gate voltage and drain voltage, and in this region I mean it is varies for both. That means, if drain voltage is changed, current will change, gate voltage is changed, current will change. Now, what happens to the third region, that is your saturated region. This saturated region is known as strong inversion mode. I mean, you have applied a voltage which is equal to V GB plus V T. So, when you have applied a voltage, gate drain voltage which is equal to V GB plus V T, no further increase in current take place, that we have already seen. So, this is represented by strong inversion mode or saturated region. Here you can see current does not change as we increase the drain voltage. Here also current does not change as we increase the drain voltage. Current is not changing at it is as we increase the drain voltage. However, it depends on the gate voltage. So, that means, in the saturated region, the current depends on both drain only on the gate voltage. On the other hand, in linear region, current is dependent on both drain voltage and gate voltage. So, we have seen the operation of these three different regions again without any mathematical expression. So, in the next lecture we shall discuss we shall derive the mathematical expression, but before we go to that, let us have a look at various parameters on which the drain current is dependent. Now, for a fixed drain to source and gate voltage, the factors that affect the drain currents are listed below. So, here we have drawn a very simplified structure of a MOS transistor. So, here it has been a 3-dimensional diagram is drawn. So, here as you can see, you have got a single MOS transistor, and this is your source, this is your drain, and this is the gate. This is the silicon dioxide, this is the polysilicon. Here as you can see, the channel has a length, that means, the source to drain, the separation between source and length is represented by L, length of the channel. On the other hand, the width of the channel, that is the how long is the drain or source, that is known as the width of the device. So, length, width, and there is another very important parameter, that is your thickness of the silicon dioxide D. So, apart from that drain to source voltage, gate voltage, it depends on this parameter, distance between the source and drain, that is your L. So, it is dependent on L, which is the distance between the source and drain, because electrons will move from source to drain, and depending on the velocity, it will take some time. So, take some time, and the rate at which it will go will be dependent on the distance. So, electrons have to traverse that distance at a particular speed, and shorter the distance, that more electrons will flow and the current will be more. And on the other hand, If the length is more, then it will take longer time and current will be less. That means, it is dependent on the parameter distance between the source and drain, the channel width W. So, more current will flow if the width is more, because you can see it is wider. It is just like a river. When the river is water, river is wider, more current, more water can flow. Here also the width is somewhat like the width of a river, and so it will be that the W parameter will be there to it will depend, the drain current will be dependent on the width of the device. Then the threshold voltage. I have already mentioned about the threshold voltage. Threshold voltage is essentially at which the onset of current, the creation of channel starts, inversion layer formation starts, and only then current flow can start, and that voltage is dependent on many physical parameters, and later on we shall discuss about this, but for the time being I have given a simple parameter, threshold voltage. Then the thickness of the gate oxide layer, this W, this D. So, smaller the thickness, even for smaller gate voltage, that control will be more. That means, the thickness will decide the electrical potential in the channel region, and that is the reason why the thickness of the gate oxide will control the flow of current, will control the flow of current within the device. And then the dielectric constant of the gate insulator. So, not only the width, but dielectric constant is also very important, and as we know, silicon dioxide is the dielectric material that is being used, but in modern devices some high K material with high dielectric constant is being searched, but for the time being we shall consider silicon dioxide as the dielectric that is being used. Then finally, another parameter is there, the mobility of carrier, how quickly it can move, how quickly the charge carrier can run. We have got two types of carrier, electron and hole, and obviously electrons being lighter, it can move faster. So, NMOS devices will be faster, as we shall see. On the other hand, holes are heavier, bulky, and as a consequence their mobility will be less. So, these are the parameters on which the drain current will depend apart from the drain and gate voltage. And in my next lecture, I shall derive analytical expression of this drain current in terms of these parameters. So, for the time being we can call it a day. Thank you.